front. So it's my pleasure to welcome today's speaker, Jim Eisenstein. Eisenstein is coming from Caltech, from a place that has nicer weather than ours. Just found out today that Jim and I have the same birthday, so that's a very good thing for him. It speaks well for him. He actually graduated from Berkeley, California. That's where he got his PhD, and from there he went on to William College before joining the Bell Labs, where he was there for quite a long time, until moving on in the mid-90s to Caltech, where he has actually created their very wonderful career, and where one of their major works has been on quantum Hall effect, showing about Topological Condensates and many exciting physics on how to actually create some very fancy nanostructures. Very, very cool, and still managing to work. The awards are very long, but the highlight, I think, here is the Oliver Buckley Prize that he received in 2007. And being the experimental of the three people that he received, so I know the other two theories that got it with him, he got the extra penny. So that's the key thing. Thank you very much. And thank you for coming, and so you don't forget us. We give you a nice laser pointer with your name on it.
Oh my gosh.
A&M in it. Nice green as well.
All right. I'll come again.
You don't get a second one.
This is great. So I should comment. First, thank you for the invitation to come here. I'm delighted to be able to speak here today. But I should point out something about this penny that you're referring to. So there was a penny involved because that got divided by 3. I returned 1/3 of that penny to Steve Gervin. I carved it out on the milling machine to exactly 1/3 of a penny. I still, however, owe Alan 1/3 of a penny, and I will when he I'm sure he does. I'll get it back to him at some point. All right, so great. So let's see if I can get this to work. All right, so what I'm going to talk about today is a quantum Hall problem at one level, but it's also more general than that. I'm going to tell you about a correlated electron system that behaves in some ways sort of like a superconductor, in other ways like a quantum Hall system. And as you can see, the title of the talk is Exciton Transport in Perfect Coulomb Drag, and you probably don't understand how that connects to the words I just gave a minute ago. Hopefully by the end of the talk you will understand. So these experiments that I'm going to describe today were done largely by Aaron Fink and Develina Nandi, who are 2 graduate students of mine. Actually, Aaron's now a postdoc at Illinois. Earlier parts of the experiments were done by Mindy Kellogg and Ian Spielman. And we have samples that are grown almost entirely by Lauren Pfeiffer and Ken West, although there have been some exceptions to that. So let me begin with the quantum Hall effect part of it, which I'll tell you right at the outset, in some ways is the least interesting aspect of what I'm going to tell you today. But we have to go through it to get the framework built up properly. So let's start by looking at this sort of canonical picture of the quantum Hall effect. And what this graph is, there's 2 traces in here. There's a diagonal one, and then there's one that wiggles a lot. The diagonal one is the Hall resistance across a 2-dimensional electron system. So somehow imagine there's a 2-dimensional electron system in this bar, and I put a current in it. I have a magnetic field, and I measure the Hall voltage across here. And like Edwin Hall found out 100 years ago, or more than 100 years ago, it's proportional to magnetic field. But then, as Klaus von Klitzing found out much more recently, there's a series of plateaus that appear, and these plateaus are quantized in the sense that they are always some rational number times h over e squared. H over e squared being a combination of fundamental constants that turns out to be 25,812.807 ohms. Exactly now. And it's used, the fact that I give you all those digits is important because the big application of the quantum Hall effect is just exactly that. It is the way we determine resistances now in all the national standards institutes around the world. So the quantum Hall effect actually has an application. Now, what are all these different plateaus? And every time you have a plateau, you notice there's a deep minimum in the ordinary resistance. That's just the longitudinal resistance. Basically, each one of these is another electronic state that has some special correlations in it. For example, This one here is the first fractional quantized Hall state that was ever discovered. It has a resistance of h over e squared divided by 1/3, which is 3 times h over e squared. And this is a many-body state. This is something which is stabilized entirely by the Coulomb interactions between the electrons. Very interesting, it's really the subject of the 1998 Nobel Prize in Physics, the discovery and the explanation of this. What are these numbers? Well, the numbers refer to the occupancy of the degenerate Landau levels of the electrons in a magnetic field. So if you have electrons in 2 dimensions and you put on a magnetic field, they go around in circles. The circular orbits are quantized. They're quantized into discrete levels, absolutely discrete in 2 dimensions. And if you have the magnetic field high enough, all the electrons fall down into the lowest Landau level. Now, the number of electrons that you have is determined by the crystal grower. The number of available states that are in the Landau level is determined by how strong the magnetic field is, and you can have the ratio of those 2 numbers be anything you like. If it's 1/3, what that means is there's 1/3 as many electrons as there are available states in that Landau level. If you had 3 times that number, you would fill up the Landau level completely. So when the Landau level is 1/3 filled, this quantum Hall state appears. Okay? We don't need to really say too much more about it than that. Notice here, at this magnetic field in the middle, where I've got 1/2 written, at this point, the Landau level is 1/2 occupied with electrons. I've reduced the magnetic field. It's 1/2 occupied. And at this point, there isn't any Hall plateau. And I just want you to remember that. When the Landau level is half filled, no quantum Hall effect. That's all you need to know about that particular configuration. All right, so that's the quantum Hall effect in a nutshell. Now, let's imagine that instead of having 1 layer of electrons, I could somehow create 2 layers. And suppose that they're identical. And I could bring them together into close proximity. And this, of course, is the magic of molecular beam epitaxial growth, that you can actually make this. But let's just say that we can do it. We can have these 2 systems, and we can bring them close together. Now, of course, the system is neutral overall, so there are some dopants somewhere, but just forget about them. They're not terribly important for the purpose that they do neutralize the system. That's an important job that they have. But other than that, they have rather little impact on what I'm about to say. We have these 2 layers, and they're close together. What do I mean by close? By close, I mean that the spacing between the layers is about the same as the average spacing between the particles. Okay, that's what close means in this context. And so you can guess that that will imply that the average repulsion of electrons between electrons that are in the same layer is roughly the same magnitude as the repulsion between electrons in different layers. That's an important figure of merit, that those 2 interactions, those 2 repulsive forces be about the same magnitude. This picture, which has got many fewer wiggles in it, this is a historical picture of the quantum Hall effect in such a double-layer 2-dimensional electron system. I've got data shown here at rather high temperature. Only a few plateaus show up. And here's one at h over 1 times e squared. But keep in mind, this is a double-layer system, and you know when you add resistors in parallel, you get a lower value than, say, if you have 2 equal resistors, you get half that value. So what this really means is that at this particular plateau, each of those 2 2D electron gases is in half-filled state. So in other words, by making this sample, I just broke the rule that I told you about a moment ago, which is that a half-filled Landau level doesn't have a quantum Hall effect. If I bring them close enough together, somehow it does. Okay, so that's the important thing. Bringing them together really changed the system in some fundamental way. Now, I'm not going to go through a complicated explanation of what all possible mechanisms for this could be. I'm going to just concentrate on the one that we think is important for our understanding of our experiments. Basically, the idea is very similar to Laughlin's explanation of the fractional quantum Hall effect at 1/3 filling, and that is to make the best possible configuration insofar as how you want to reduce the repulsion between electrons. That's your goal, after all, is to reduce the energy. So what do you want to do? You want electrons that are in the same layer to efficiently stay away from one another. That makes good sense. But they also want to stay away from the electrons in the other layer. And if you can do that in a particularly efficient way, and I've got a complicated-looking function here that does that, then you will establish this quantized Hall state. Crudely speaking, this picture kind of illustrates what's going on. In this layer, which is a cross-section, the red layer, I have electrons that are occupying half the available states. The open circles are supposed to be empty states. So it's half filled, as you can see from the picture. Same thing's true in the blue layer. But because the layers are close together, the electrons in the red layer always manage to look to be situated, momentarily if you like, opposite a vacancy in between electrons in the other layer. That's the correlation that we think is responsible for this state. Now, don't take this picture too seriously. It's not ordered in a static way like this picture would make you think. But if you found an electron in one layer and you could instantaneously look in the other layer and say, is there an electron there? You would say, the answer would be no. There would be no electron. You'd be guaranteed that. And similarly, if you found an electron in the opposite layer, you would at the same time find no electron in the other layer. So there's a very strong anti-correlation between these two layers. And it's because the system wants to reduce the Coulomb interaction. Now, I showed you at the beginning that if you have one layer, this 1/2 state does not occur. So it must be true that as I make the layers farther and farther apart, that this state will go away. Because if they're far enough apart, they're just two independent layers. Can't matter anymore. And you can have a long discussion, and many interesting experiments have been done to sample, well, just exactly how does that transition occur? Is it a phase transition? If it's a phase transition, what kind of phase transition? A lot of interesting physics here. We do believe it's a phase transition, and I've kind of indicated that by this picture, which is a phase diagram with one dimension, which makes it simple, just the spacing between the layers. There are many other directions you could go in phase space. You could try changing different parameters, Zeeman energy, all kinds of different things. But let's forget about all that and just say the simplest parameter I can think of is just literally expand the layer separation until the state disappears. Turns out it disappears essentially at a critical point. Okay, so we know that transition occurs. All right. Now, this is very interesting. We've spent a lot of time, more years than I would like to admit, in studying this. Even before you were born, I think we were actually already working on this. It was sort of a birthday celebration for you. So how do we want to think about this state? There are multiple descriptions that you can use, and I'm going to use one of them for the purposes of today's talk. So again, what I started off with was imagining two layers that were identical, and both of them in this so-called half-filled state. I can, if I like, choose to make something called a particle hole transformation, the same thing that you do when you talk about the valence band in an ordinary semiconductor. I'm going to concentrate not on the electrons in layer number 2, but on the holes that are there. I can do that. If I choose to do it in that way, it sort of makes sense that the electrons in layer number 1 bind onto the holes in layer number 2. That's this anti-correlation that I told you about. And all I have to do is remember to carry around, just like I do in ordinary semiconductor physics, a filled valence band, sort of in my back pocket. If I look at it from this perspective, this state that I wrote down that wave function for really is equivalent to this. And you think, well, what the heck is that? Basically, this is essentially almost identical to the wave function for a BCS superconductor, with the important difference that the Cooper pairs that you have in a superconductor, of course, consist of 2 electrons. Here, the Cooper pair is an electron in a hole. Okay, so you can imagine, and many people did in the years immediately following the BCS theory, said, wait, we can make some kind of BCS theory out of excitons. Here we're going to talk about just exactly that. With the different, and it's an important difference, is that there's a very large magnetic field applied here, perpendicular to the plane. So that's the name of the game. This is what this wave function describes. It's really a BCS wave function. An important part of BCS physics, or superconductivity, is that you have phase coherence. There's some kind of macroscopic phase that the superconductor, or in this case the excitonic Bose condensate, acquires, and that phase is presumably coherent over long length scales. And how much evidence we have for that is something that we can talk about. Okay, so what do we know about this system? And I'm still talking about, at a conceptual level. So it turns out that there are 2 modes of transport in this system, transport of electrons or excitons. As in a superconductor, you have a condensate of Cooper pairs, and you also can break Cooper pairs and have quasiparticles above the energy gap. Those quasi-particles can move around. Usually you don't think about them too much because they're shorted out by the condensate, the superconducting condensate. In this case, if I drive electrical currents in the same direction in the two layers, it should be clear to you that I can't do that by transporting excitons. Excitons are neutral objects, electron hole. If they transport this way, that doesn't correspond to currents going in the same direction because they're oppositely charged particles. It corresponds to currents going in opposite directions. This transport can't be occurring in the condensate. It must be occurring among the elementary excitations of the system. And it's very interesting. It is the transport mechanism that's responsible for the quantized Hall effect, but it's occurring not in the condensate, but in the elementary excitations of the system, and they're complicated objects that I'm not going to talk about. You might be wondering, well, what am I going to talk about? I'm going to talk about this. This system is, again, like the case of a superconductor. You have a condensate, which can carry supercurrents. In principle, this system should have a condensate that contains only excitons, and they should be able to move. If they move, say, from left to right, that would correspond, at least at the superficial level, to a current going from right to left in one layer and left to right in the other layer. If I can do that experiment, by making that happen, I might be able to establish that I'm actually transporting excitons. Okay, that's the object. That's a condensate mode of transport, and that's what we're after to try to see if we can detect that. All right, so let me give you some evidence of something other than the quantum. Remember, I told you a moment ago that the quantum Hall effect, in some sense, is the least interesting aspect of this system. So what are some of the more interesting ones? Here's an example. And this is a cartoon, but it's a remarkably accurate cartoon. We have the two layers. We make a contact only to the bottom layer over here on the left, and a contact to the top layer over here on the right. And don't worry about how I make these breaks in here, but we do it. And then we hook up a battery and set up an ammeter, and we try to measure whether current flows. If current were to flow from this battery, it must be doing so by tunneling across this barrier. Okay, it can tunnel. We can determine how much tunneling there is. We can grow samples that are weakly tunneling, samples that are strongly tunneling. All depends on how thick the barrier is, how tall it is, the usual things. Suffice it to say that we start with samples which have extremely little tunneling. You can never make it zero, but we try to make it very, very small. We make it small so that tunneling is really not relevant to the condensate physics itself in terms of the stability of this phase. It's a very, very weak effect, but it's not zero. So we can use it as a probe. Okay? Just like tunneling was used as a very efficient probe in understanding BCS theory back in the early days. So what happens if you do this experiment? Well, here's a picture. So there's two traces here, a red one and a blue one, and there's my phase diagram. I've got the critical point marked by the green line, and I have a blue dot and a red dot. These are actually the same sample. Let's not worry about how I managed to make it go in both places. But I start with the blue dot. The sample is above the critical point, and I measure how much tunneling there is. Okay, I do the battery and the ammeter, and I just measure it. And I find out that it looks like this funny blue curve, which won't mean a lot to you, except you can concentrate on one part of it. Down here, when there's not much voltage applied, the tunneling conductance, the inverse of the tunneling resistance, is zero. The blue curve is just flat, and it's just zero. Tunneling is just almost absent, heavily suppressed. It's very hard to tunnel if I'm up at the position of the blue dot. But if I go to the red dot, that happens. This surprised the daylights out of us when we first saw this, that by crossing this phase boundary, all of a sudden the tunneling got just inverted and became very, very strong. You might ask yourself, well, why is that happening? We did better and better experiments, and it got, more and more dramatic. There's the tunneling resonance. It's a microvolt wide. It's incredibly narrow. We don't even know how narrow it really is. It's very, very tall. We believe that fundamentally what's going on here is that because of this electron hole coupling, an electron which wants to tunnel across already knows exactly what's going on in the other layer. There's a hole waiting for it to jump in. That is a very qualitative thing to say, but it's not so far from the truth. In fact, if you think about this wave function a little bit, you'll conclude that there's no energy cost whatsoever in taking an electron and moving it from one layer to the other because of this correlation that is built in. If you're on the wrong side of the phase boundary, well, then there is a cost. You have to pull it out of one layer and stuff it in the other layer. And that costs energy. Does not cost any energy when this correlation is there. Okay. So this was great, and we thought this was a very strong indicator that this phase transition had occurred. I'm not going to show that. I'm going to skip that for now. Let me talk about another experiment. So I told you that there's putatively this mode of transport where if you could get the currents going in opposite directions, that might be carried by these excitons going along, and that would be nice to detect. So we just set up this experiment. There's the active region. This is a photomicrograph from the top. The active region is in here, and this is Mindy Kellogg's thesis experiment. What she's doing is driving current through that region. I think this is one of the two layers. Let's call it the top layer, and it's going from right to left. Then it comes out. Over here we measured it to make sure that it's all there. Not so obvious. Comes back, and it goes in the opposite direction, but it's in the other layer. I have a way of making sure that I know what layer the currents are flowing in. This is a technical thing, and we know how to do it. And I'd be happy to talk to you about it later if you're interested. If we didn't know how to do it, all of the experiments that I'm going to describe today, with the exception of the quantum Hall effect at the very beginning, would not be possible. Oh, it's essential to be able to get a hold of the individual layers. Okay, so what happened when we did this experiment is the following. That we measured the Hall effect in one of the two layers while we drive the current in this counterflowing geometry. All right, simple enough to imagine. If these were two ordinary plates of metal where you just connected them together with a wire, well, you'd see the Hall effect in the blue metal, and the yellow metal would have no impact whatsoever. It's just the return path for the current. Either layer. So I'm just showing a picture here where I've measured the Hall effect in the so-called top layer in this picture. And what I find is that at low magnetic fields, where I'm not in this exotic phase, well, I just get the standard result. I see the Hall effect of the blue layer by itself. But at 2 Tesla, it enters this special state. And now you notice the Hall effect vanishes. So the Hall effect is something where you put on a magnetic field, and if the magnetic field is big, you usually get a big Hall resistance. And if you have a really low density system, and believe me, these are very dilute electron gases, much more dilute than Edwin Hall had when he was playing around with gold foil, the Hall voltages are generally gigantic, right? 25,000 ohms. They're very big Hall resistances. It's zero. Zero. Okay, so this makes you think, my goodness, it must be that this transport is occurring via excitons. Okay? Because excitons are neutral. There's no Hall effect because the Lorentz force on the electron is canceled by the Lorentz force on the hole, and everybody's happy. And now an answer to your question, which I think you were going to ask, is if I measured the Hall effect down here on the other, it also gets zero. Well, this is not due to some funny cancellation of the Hall effect in one layer being the opposite sign of the Hall effect in the other layer. That's not what's going on here. All right. So I just said that. All right, so at this point you might say, you declare victory and go home. And we were very tempted to do, not to go home, but we were certainly declared victory. Problem is, and this is what the talk is really about, is that this line of argument is very nice and very circumstantial. And I'm going to try to explain to you what I mean by that, by it being circumstantial. And to do that, I'm going to put up this picture. So probably the most in vogue thing going on in condensed matter physics today are topological insulators. And let me just tell you what they are from my perspective. They are materials which are insulators. That's part of the word, part of the phrase. They're insulators in the bulk. If you could get inside, away from all the boundaries, it would be an insulator. No charge could be transported. However, being topological insulators, they have a conducting state that exists on the boundary. And in 2 dimensions, that boundary is just a line. Here I've got a circular sample. There's some conduction occurring along the outside. And for all the people that know a little bit about the quantum Hall effect, You've probably heard of something called edge states. Well, that's what they are. They're out there at the edge, and they conduct. The bulk does not conduct. Okay, so if you make a measurement of, in an ordinary sample, a simply connected sample, topologically simply connected, and I put the current in over here on the left, and I take it out on the right, and I measure the voltage across, well, that's the Hall effect. What am I going to see? The ratio of the voltage of the current will be h over E squared. That's the Hall effect. No surprise there, because that conducting edge channel makes it so, even though the bulk is insulating. Right? Quantum Hall effect's really insulating, topologically. It's so insulating in the bulk that if I drilled a hole in the sample and literally drilled a hole in it, nothing would happen. Okay? The bulk has no impact. Unless the hole is so close to the edge, we might have a problem. Right? But if I drill a modestly sized hole, it will have no impact whatsoever. Okay? Now, this is important. Now, let's do one more experiment. Let's ask what happens if I try to measure how much conductivity there is between, now it's multiply connected because I drilled the hole, from the outside edge to the inside edge. Well, I just got done telling you it's an insulator in the bulk. Charge can't go across the green area in the bulk, so you better get 0 for the conductivity in this experiment. This is something called the Corbino geometry, which I think I learned from Marco. That Corbino was Fermi's teacher, right? Did I get it right? Something like that, right. Anyway, so people do this experiment. We've done it for many years. This is called the Corbino experiment. And what you measure is the conductivity of the bulk. It's a function of magnetic field. You go into the 1/3 state, for example, and it's 0. Because the 1/3 state's a quantum Hall state. The nu equal 1 state, this is a single layer right now. It's 0. Bulk is insulating. If you're not in the quantum Hall states, well, then it's conducting. Weakly, maybe, but it's conducting. Okay. In particular, if you go to half filling, once again, for a single layer, there's no quantum Hall plateau there. I told you that right at the beginning. So it's a conductor at that filling. There it is, not 0. All right. So we come back to this experiment. This is what we did, and I didn't mention the edge channels when I talked about it. So what role are they playing? This was not a multiply connected geometry. These contacts were all on the outer boundary. Excitons, presumably, well, they're neutral. They should be able to move throughout the bulk because they're not charged. If they can move throughout the bulk, they're not transporting any charge, so the fact that it's an insulator in the bulk is not relevant. They should be able to move through the bulk. But these contacts are on the edge, only on the outside edge. So they can never tell you whether or not the excitons moved through the bulk. Okay, so again, those early experiments were consistent with their interpretation, but we didn't really know what the role of the edges were. For that reason, we have to do with this experiment. And this is where the new data that data we've accumulated in the last year and a half or so is going to come in. 2 layers, right? Multiply connected. I drill a hole through both of them. 2 donuts, one on top of the other. I place contacts. Oops, I haven't done it yet. There, I placed contacts. 2 on the outside, 2 on the inside. They're not exactly laid out like this, but for the purposes of this talk, they are. I'm going to show a number of view graphs in which you see a picture like this. And what I want you to always make sure you understand is that the contacts on the left are not on the same edge as the contacts on the right. That's extremely important. Okay? They are connected only by an insulating bulk. Well, the first experiment we can do is this one. Let's see if, in fact, we measure any current through the bulk. This experiment, you would agree, if I put a battery here, would try to drive currents in the same direction in the 2 layers. I just got done telling you that it's a topological insulator, so there better not be any current flow. And we go and we find out this is the appropriate magnetic field. That's the state in question. It's an insulator. We knew that was going to happen, but we wanted to make sure. Okay, so no current flows if you try to drive current in parallel. Okay? It's not a problem of the projector. It's a problem of the sample not having as high a quality or as big an energy gap as we would like. Yes, I wish that was even deeper, but it's not. So it's small, it's thermally activated, it has all the right properties, but no, it's not zero. I mean, heck, it's not zero here either. It's just a lot smaller than you're willing to look at. Why this is so fat? It's just quantum Hall physics. There's a huge energy gap here. This is filling factor 1 per layer, the gigantic energy gap. This is filling factor 1 of the double layer system. And 1 is equal to 1/2 plus 1/2. Right. This is actually filling factor 2, which is 1 plus 1. I learned a lot about arithmetic from doing these experiments. Believe me, I didn't learn it when I was in elementary school. I guarantee you that. All right, so that's fine. Now let's do some more experiments. So we learned that it's an insulator. We know that. We knew it was going to be anyway, but we proved it. So here we are. We set up this experiment. We can do all the different kinds of, you can do whatever you want with these various contacts. This looks like a tunneling experiment, right? I put the battery between the two layers and I tried to see if any current flows. And I showed you earlier on that there was this big enhancement of the tunneling, and now it doesn't seem to be there anymore. Well, I killed it. I did it on purpose. I wanted to kill it off because I wanted to make sure that we were sensitive to exciton transport and not just plain old tunneling. How did I kill it? Well, I killed it by doing that. Taking the magnetic field, and let's not go into this, but taking the magnetic field and tilting it a little bit. The added magnetic field in the plane suppresses the critical current for tunneling just in the same way, for those of you that are superconductivity aficionados. You remember something called the Fraunhofer Pattern for a Josephson junction. You put magnetic field in the plane and the supercurrent drops away because of the phase that you've injected between the two layers. And we're using that essential physics to wipe out the tunneling. Not completely wiped out, but it's, and in fact, if you've got lover's eyes, you can see there's actually a tiny little step in here, right at the origin. But it's very tiny current. Okay? Good. Now, I'm going to make one change to this circuit. I'm going to come along, and I'm going to short circuit those two contacts together. They're on the other side of the insulating desert. Right? Nothing should happen. Lots happens. All of a sudden, current starts to flow. It wasn't flowing before. Now it's flowing. This is completely different than this. But they're not connected by edge states. There's only the insulating bulk in between. So you say, what is going on? Well, all right. The first question is, maybe somehow this remote short changed my understanding of tunneling while I was out having lunch, and made the tunneling turn back on. So a huge current's flowing, and it's not going here, it's just somehow tunneling in between. No, everything is now tilted. Field is tilted. Field is tilted to kill the tunneling. All right, well, what do you want to do? Actually, I've gotten ahead of myself, and I'll come back. So here we've done two experiments. The first one, I showed you, no current flowed. Call that parallel transport. It's an insulator. This one, lots of current flowed. Imagine trying to build a device that did this out of conductors. You can't do it. These things seem to be paradoxical and contradictory. If this doesn't carry current, how in the heck is that going to carry current? That's the puzzle. It does it because the layers are not two independent conductors. They're one system. All right, so I ask you about enhanced tunneling. I mentioned this is why I said it. These view graphs are slightly wrong order. Maybe some enhanced tunneling turned on while I wasn't looking. Well, there's an easy way to determine whether that's true. Try to measure whether there's any current actually flowing through this shunt. You can measure that. So we do that. That's easily done. And we find out that the current that flows through the shunt is exactly equal to the current that flows from the battery. So somehow it didn't tunnel. It actually got all the way over there through the insulating desert and went through the shunt. And it did so purely because the currents are flowing in opposite directions in the two layers. When they flow in the same direction, I already proved to you that no current flowed. Now, I don't have the data here, but I should have brought another view graph. A big, amazing fact is if you try to take a wire and place it from here back over to the back side of the battery. If these were two ordinary metals, 2D electron gases are very highly resistive. The current would say, well, geez, it would be ridiculous to go this way. I'll just go through the short circuit you just provided for me. And we did that experiment. No current flows through the short circuit. No current goes through the short circuit. It only will go if these two currents are equal and opposite in the two layers. Okay, so that's that's an important factoid. All right. So what have I shown you so far? Counterflowing currents can pass through the insulating bulk. They don't transport any charge, right? The two currents are equal, but opposite. So no charge is actually going anywhere. So it's not inconsistent with the system being an insulator. Parallel currents cannot cross the bulk. Counterflow transport is exciton transport. How's it working? Well, this is just a cartoon. There are a lot of cartoons today. So I could imagine two regions of my sample. Part of it over here on the right is where I am in the coherent state. But don't worry about how I do this. This is a Gedanken experiment. Over here, it's the coherent bilayer in this excitonic phase. Here, the layers are somehow independent. If I bring an electron in from the left, this is what it does. It launches an exciton and reflects in the opposite layer. This is a picture that's really come out of Alan MacDonald and his group. This is Andreev reflection, or the analogous effect with excitons rather than Cooper pairs. I'm launching these excitons by sending current in, and it's reflecting in the opposite layer. So think about it for a minute. Here's my circuit. I have these two layers. I got a battery here, and I've got a resistor here. I got an insulating material in between. But nonetheless, I can transport excitons across. They're neutral. I can take energy from the battery and dissipate it in the load without transporting any charge. Next question is, well, I told you this is kind of like a superfluid or superconductor. Is the exciton transport super in any sense? This has turned out to be very hard for us to determine. We have various experiments that impact this question, but none have been what I would call incisive experiments that really nail it. What we've tried to do is to determine whether or not, well, quite simply, that relationship is true. Is V equal to IR? Well, if there's dissipation in between, then V would not equal IR. V would equal IR plus that extra dissipation. So if I could just figure out the circuit completely, I might be able, and measure these quantities, I might be able to answer this question. This turned out to be rather hard. Knowing, I've drawn the cartoon here as though this is the only resistor in the problem, and unfortunately there's resistors all over the place, in the contacts, in the wires, in the arms, all various places, some of which are not well characterized. So we do our best, and I won't go into the details of how we do our best. All we can do is estimate so far whether V is equal to IR. And we find out that in one case we actually measure, in the other case we estimate, this estimated intrinsic voltage drop. What I'm trying to say, and I'm saying it clumsily, is that here I've got a battery, there I've got a resistor, current is flowing. If it's a superfluid, right, V is equal to IR. What we've tried to do in this estimation is to remove all the extrinsic resistances, which are not shown in this picture, and subtract the voltage drops that are occurring in those extrinsic, uninteresting resistors. And to the ability that we've been able to do that, all of the voltage drop supplied by the battery is falling across the extrinsic resistances. None appears to be falling across the actual exciton channel. How accurate is that? Not very. But it's the best we've been able to do so far. Okay, so let's keep going. And I'll put up some more kind of provocative things. So here's another analogy to superconductivity. My system is not a superconductor. It's got these excitons in it. They're neutral. But it's kind of a superconductor. So imagine that you wanted to solve the world's energy crisis and you did it by creating superconducting transmission lines so that, the power supply, wherever it is, can make your toaster work in your home by supplying current to it. Don't forget that the current has to come from the power supply to the toaster and back from the toaster to the power supply. Right? There's always two wires. Counterflow. It's like counterflow. I have to have current going like this, go around and go back. These are independent superconductors. My system is one thing. But nonetheless, if I look at this and I ask, what is the superconducting phase? Well, it's got two terms in it. It's got a time-dependent term coming from the battery voltage, that's the Josephson relations, and it's got a gradient in space because I'm actually transporting current. That's for the case of two superconducting wires. What about this case? This is the case we're working with. It's one system that consists of two intimately connected layers. It's just one thing here. There's not two superconductors, it's one. But it acts in exactly the same way, or so we think. And the phase of this fellow also looks exactly the same way. So in some sense, this behaves really just like a superconductor delivering energy to a load. Okay? All right, now, I think it's pretty obvious. At some level, it's misleadingly. Yeah. That's right. So if I have a voltage between these two layers, the phase of the order parameter is going to precess. There's still a Josephson relation. That's true, but I have two layers of electrons, and if I make a voltage difference between those two layers, the order parameter is going, I'm just repeating myself. The order parameter is going to rotate, the phase is going to rotate, and it will do so in this fashion. There's no 2E here. Sorry? I don't look at it that way. I don't look at it that way. I say that EV is simply, well, EV. I have a battery. No, not at all. It's a voltage between the two layers. That's it. Could be zero, could be small, could be big. It has nothing to do with the underlying energy gap of the system. In fact, it's generally quite small compared to it. Yes. So that would be a wonderful thing to do. The answer is probably no. In fact, I'm sure it's no, because there are contact resistances that I've kind of alluded to associated with getting current to go in and out of quantum Hall systems that you can never get around. No matter how well I design the circuit, I'll always have something of order h over e squared in those contact resistances. So let me go on with this for a minute and say the following. It's pretty clear that the way I wired it up by making that circuit, it makes it look obvious that the currents are going to flow in opposite directions. I'm kind of wiring it up so that they should do so. So let's talk about doing it a different way. Let's talk about something called Coulomb Drag. This is the second half of the title of the talk. What the heck is Coulomb Drag? Let's get on the ground and know what it is first. Two conductors close to one another. They could be pieces of copper. I put a current in one, and I try to measure whether a voltage appears in the other one. And if there's an insulator between them, well, there is a voltage if you get very, very good measurement, but it's extremely small. Electron-electron interactions between the two pieces of copper will produce a slight tendency to deliver momentum from the current-carrying piece of copper into the non-current, and it'll build up and produce a voltage. And with copper, forget it. Don't ever try to do that experiment. You'll never find it. But you can make systems in which it's a detectable effect. We've done that. Semiconductor systems. Copper is just too much screening. You'll never see it. Okay? We did this experiment a long time ago. There's some data. It's a very pretty experiment, actually. The drag current, or the drag voltage, here's the voltage on one layer, the current is in the other layer. The voltage vanishes as t squared. This is a direct electron-electron scattering process, and you're measuring that scattering time. I don't want to go into those details, but we've spent quite some time on this over the years. I'm going to skip this picture, and I'm going to skip that picture and go to this one. I'm running out of time. Let's go back to the system in question, the donuts. Green donut and yellow donut. And I'm going to hook it up like this. Look at the circuit. Different than the circuit I showed you before. There's no connection between the two layers. right? No connection. There's a battery trying to drive current across the insulating bulk of the green layer, and another, not a battery, a resistor that simply shunts the inside edge to the outside edge of the other layer. Yeah, magnetic field is perpendicular. And I'm in this exotic state, and I've got everything tuned up just right. Okay? Okay, so you do this experiment. First you do it AC, and we'll talk about the DC results in a minute. This is the magnitude of the current that's observed in the layer that's shorted to itself. Well, most of the time it's just zero. If I got a real microscope out and did the experiment even better, I'd probably find a tiny little effect there, but it's extremely small. When I get to this magic filling factor, 1/2 plus 1/2 equals 1, something happens. And now current is flowing in that layer. You do it more carefully and look more carefully, and here's what you find. The current in the drive layer, that's the one that's got the battery in it, and the current in the dragged layer at small amounts of battery voltage are exactly equal. As best we can tell, they're exactly equal. But I didn't show, this diagram doesn't show, they're in opposite directions. Right? The electrons are going along like this in the one layer, and from an electrical perspective, the current in this layer is, well, actually, the electrons are going this way. The current's like this. I'm so excited about this that I knocked the thing off. It's really exciting. You should all do it. Let's see here. Maybe that will work. The current in the opposite layer, the other layer, is flowing in the opposite direction. Normally, when you do this drag experiment, if you can even detect the effect, well, the currents would flow in the same direction for two equal metals. Right? One current delivers some momentum to the other layer, and it kind of drags it along. It goes in the same direction. These are two electron layers, and yet the currents are flowing in opposite direction. How is this happening? It's happening precisely because there are excitons in this system. In other words, this was what I showed you before, and I showed you that silly cartoon. Then I showed you this. And what's happening is exactly the same thing. But there's no wires connecting the layers anymore. Right, you're banging your head. I bang my head a lot about this. Right? Excitons are being transported. In this case, I drew it as though they're going from left to right. It's the only mechanism that can get across the insulator. It's the only thing that can make it across the insulating bulk. And it's equivalent, if you like, to oppositely directed currents in the two layers. So yes, indeed, we measure that I2 is exactly equal to I1. And I've got them going, the arrows are in the right direction so that they're actually pointed oppositely. Why do I call it drag? Well, why not? Well, it's Coulomb interactions, right? It's only Coulomb interactions, and it wouldn't, I mean, that's all I can say, really. I mean, I think that's semantics, I believe. Okay, let's call it something else. I don't care what you call it, but it's perfect. It's perfect in the sense that the two currents are equal. They're opposite directions. The electron's going along and it's dragging a hole with it. So of course the currents are in opposite directions.
That is what you observe?
Yes, it's exactly what we observe. That is exactly what we observe. That's the whole point, is that the currents are equal and equal in magnitude and opposite in direction. Now you noticed a minute ago I showed you the graph, and they were equal down at small voltages, and then they became unequal. Right? You probably saw that. Now, why would they become unequal? Well, it turns out. I'm sorry? It's better when you're cold. So that's a really good question. So when I talked earlier on about the phase diagram having many axes, one axis you could explore is temperature, and we frankly don't really know. There's a strong temperature dependence. Above, say, 200-300 millikelvin, this effect disappears. Does it look like, is it a sharp thing? No, it's continuous. Is there really a phase transition going on in this system? At the theoretical level, there should be. Experimentally, I would say most people would say, I don't really think you can say one way or the other. At best, it's Kosterlitz-Thales. So it's Kosterlitz-Thales, and furthermore, there's a little bit of tunneling. The fact that there's a little bit of tunneling means Kosterlitz-Thales doesn't really work. So this is a difficult issue that we don't know the answer to. Good question. All right, so and if I raise that temperature, those two currents become unequal. I'm about to show you that. This graph shows you the ratio of the two currents as a function of temperature and a function of voltage. If the voltage is small and the temperature is small, the two currents are almost exactly equal, 97%. So it's almost perfect drag, or perfect whatever you want to call it. Perfect exciton transport. But it's not exactly perfect, but darn close. And Marco asked the right question early on. He said, why isn't the minimum of the conductivity thing that I showed you, why isn't it more close to zero? Well, and I mumbled something about sample not being perfect and so on and so forth. There is a small amount of conductivity through the so-called insulating desert. It's not exactly insulated. And you're putting a voltage across this device. So in fact, some amount of current will flow that's just plain old current, charge transport. So if you analyze these pictures, both as a function of temperature, you notice that the ratio rapidly quenches. By 100 millikelvin, there's nothing there. It also quenches by putting on too much voltage. Both of those things make the conductivity of the so-called insulating desert get spoiled. So we can model this rather easily by including in a very simple theoretical argument both parallel conductivity due to charge and superfluid conductivity due to the exciton transport. And at least at the semi-quantitative level, we can reproduce these curves. So what they represent is the fact that in reality, both modes of transport in general are active. And what you want to do is go to the lowest possible temperatures with the lowest conductivity, most insulating bulk, and you will see drag that is perfect. And this data, I think, demonstrates that that's what's going to happen. What does happen? Another good question. So no, we don't see any evidence for a critical velocity. I think I'm not going to show it, but if we measure the charge conductivity across the device, it's a nonlinear function of voltage. This is quantum Hall breakdown. So in fact, the conductivity, that minimum, gets rapidly shallower if you just push too hard. Too much voltage, current's going to flow. The insulator breaks down. And that's sufficient to understand this. We don't see any critical velocities. It's a great question because we would like to look for them in the analogy to critical velocities in helium or in superconductors. All right, so I'm finished now. So let me just wrap it up. Say that I believe that these recent experiments for the first time have directly demonstrated that neutral objects go across the bulk of the sample. We were not able to conclude that from the samples on the simply connected geometries. We have shown that we can transport energy across. We can heat up the resistor that's on the other side of the insulating bulk without actually transporting any net charge over there. And the drag is perfect at low temperatures, low, closely spaced layers, and small voltages. So the big questions there are a lot of big questions that remain that we don't have answers to. One of them is that the dissipation, we know the dissipation in exciton transport is small. That doesn't qualify for the word superfluid. So we're doing our best to find out how small is small, but that's going to be a long road. In fact, these experiments are probably not the right kind to try to answer that question. The question of the coherence of the exciton transport and how long the coherence length is, whether we have a coherent phase across the entire sample, is also a tough question. And we seem to find, I didn't discuss it, but there's some evidence that it is pretty coherent, even over, by the way, the sample's a millimeter in diameter, it's huge, that it is, in fact, coherent. And the last question is very hypothetical, is that can we make what I would call, and Xiaogang Wen was the one who put this idea out the first time, could I make an excitonic Josephson effect? Well, what is the Josephson effect? You have two superconductors, and a Cooper pair goes across with no voltage applied. Can I make two of these systems edge to edge like this and transport an exciton across. Not charge between the layers, which is what I've shown you, but exciton transport in the plane through some barrier. This would be a neat experiment to do. We're nowhere near ready to do it. But it's something that should, in fact, work. But we, as I say, it's very, very hard to imagine how to design a controllable or a controlled barrier between these two correlated electron systems. Okay, I'm finished. Thanks very much for your attention. Okay, so I don't know why this may do this for the rest of the week. I don't know how to turn it off. So yeah, I didn't say anything about the material science part of this. So these are semiconductor heterostructures. There's 2 quantum wells of gallium arsenide that are about 150 angstroms thick, and they're separated by a barrier layer of aluminum arsenide, which is about 100 angstroms thick. So it's a double well potential, and each one of the wells has been doped by some dopant atoms, which are far away, that dump electrons into the lowest quantum state in each of those quantum, particle in a box states in each of those quantum wells. Now, they're very close together, and normally when one makes an electrical contact to such a system, the way you do it, the way we've done it, is you take some metal, indium or gold, nickel, germanium, there are various recipes you can look up, and you put it on the sample in some location, and you turn up a furnace, and you heat it, and it diffuses in, dopes like crazy, contacts both layers, right? It's almost, you can't stop diffusion on a dime like that. You could imagine trying to etch away chemically the top layer. That's a completely fruitless way to try to do this. So you have to come up with a better idea, which we came up with 22 years ago. And the better idea is the following, that these electron gases have, they're pretty low density. They're maybe 10 to the 10th or 10 to the 11th per square centimeter electrons. Suppose I have 2 of them here, and I have a contact at the end of my fingers, and I take a metal plate, and I put it above it, and I put a battery between that metal plate and this double layer system. Well, it's really a capacitor. Here's the metal plate, here are the 2 layers, there's the battery, charge gets transferred. This is something we do all the time. It's called gating. If I turn up the battery in the negative direction, it removes carriers. And if you think about it, and this is freshman physics, if those 2 layers are together, connected together, initially, all of the charge is going to come out of the layer that's closest to the gate. It's completely screened. I mean, this doesn't actually happen, but it's very close to what happens. Classically, that's exactly what would happen. So you just keep turning up the voltage until this layer shuts off. And then you turn it up a little more to make sure nothing nasty happens. And then this layer remains conducting. If you turned up the voltage some more, eventually that layer would cut off. And we do that too sometimes for other purposes. So if I do it in the way that I described, I end up with my contact only talking to the rest of the universe, which is over here, through the bottom layer. And I can put those, what I didn't tell you is that these samples are, they start off the thickness of 0.5 millimeter, and then we chemically thin them to the thickness of about 50 microns, about the thickness of a sheet of paper. And we put metal gates on both the front and the top so that we can either cut the bottom layer or cut the top layer by applying these depletion voltages. So now you can imagine what we do. And it's a nasty business, but it works quite effectively.
In your first experiment, when you have the, I'm sorry.
Then ask the question.
In your first experiment, when you have the Andrei reflection,
Right.
It's also periodic process. You probably can find some special method. Electromagnetic oscillation, because you have 0 total current up to some moment, and then reflection gives you non-zero current.
I'm not understanding.
Periodic, or it is not periodic?
No,
Not periodic.
not periodic.
already somewhere in your picture.
We've done no AC effect experiment.
You showed dramatic narrow peak in charge. How this peak, but this peak depends on temperature and other parameters on the side. What is the
So what we find is that the peak is very narrow and that its width grows roughly quadratically with increasing temperature. We don't know, we lose the ability to answer your question when we go to the lowest possible temperatures. We've made, the data that I showed with this sharp peak was what's called two-terminal data. When we do the experiment four-terminal, the width of that resonance is below a microvolt. And frankly, we don't know whether it isn't just zero. In other words, if I look at the IV curve, instead that was VI dV to make the peak. If I look at IV, it's a virtual discontinuity. Now, virtual, what do I mean? I mean, I don't know the answer. It's extremely sharp. I'm sorry? Well, that's another good question. So the data that exists in the literature suggests that the magnitude of the jump in the what you might call a critical current, the integral of that sharp peak, is proportional to the area of the sample, which may sound like, well, that's the most obvious thing in the world, and it turns out it's not at all obvious that it should be that way, for reasons that we could talk about later if you want, but they're not obvious that it should be that way. It does, in fact, appear to be the case that it is proportional to area. Yes, it's absolutely collective tunneling. It's absolutely collective tunneling.
So if you push the analogy farther to the conductor, is there an equivalent of the Meissner effect problem?
So I'm not the right person to ask this, but I can refer you to the literature in which, back in the early 90s, Francis Uzawa in Japan published some papers where he said there was, in fact, a Meissner effect. And in fact, careful looking at that by Alan and Steve, they wrote another paper and said, no, there is not a Meissner effect in this system. So I might put my money on them. I think the answer is no, that there is no Meissner effect.
Are there any novel applications when you make one layer have plus delta and the other layer have minus delta?
Good question. So you mean a half plus delta and a half minus delta? Right. So here's the interesting thing. If you think about it for a minute, you realize that what's important here is not that it's 1/2 plus 1/2. What's important is that it adds up to 1. So in fact, if I have 1/2 plus delta and 1/2 minus delta, those still add up to 1. So this system is robust against charge transfer between the two layers, and that's experimentally demonstrated to be the case. Obviously, if you make too much charge transfer, various other things can happen. For example, if you go to 2/3 plus 1/3, who wins, Bob Laughlin or the excitons? There's two phases there. In fact, we've seen the phase transition between what we call the double layer Laughlin state and the excitonic phase. So
that means that not all electrons and holes will be there.
right, I mean, in that case, it would be two independent layers deciding that it's much more sensible to make individual Laughlin states than it is to do this exciton nonsense. I can't guarantee you that this phase is always the lowest in energy of all possible correlated phases. Yes. I believe the answer to that is yes. I'm not a theorist, but I believe the answer to that is absolutely yes. I'm looking for a picture of the Josephson effect, and I can't find it, so you're out of luck. Sure. Oh, yeah, you guys got good eyeballs. This one? This one? Okay, so like I said, you guys have got good eyeballs. So keep in mind, first thing to say is this is not the tunneling current. This is the tunneling conductance. This is di dV. Nobody says di dV can't be negative in response to a voltage. That's the first thing that's important to say. I never goes negative relative to the voltage. I always stays positive. But that doesn't mean that if I increase a voltage, the tunneling current might decide to go down. And if it goes down, well, then di dV has become negative. Now, the other question that this picture raises is, what are these bumps? Just what are they? And you can see them in the blue trace, and then in the red trace, they've just kind of moved in, and they're there. What these things are is they are remnants of the tunneling response of a single layer. In other words, imagine bringing an electron from outer space and slamming it into a 2D electron gas. If you go in at very high energies, well, sure enough, you're going to be able to get in. If you push hard enough, you can open the door. If you come very gently, in other words, at low voltages, the electron gas says, no, you can't come in. So this is what we call these things the incoherent tunneling signatures. They have nothing really to do with the bilayer aspect of the system. They're present even for single layers. And in fact, you can see that here in this picture. I didn't show this one. This is the integral of the IV curves, of the dIdV curves. So this really is I. It's not actually integrated. We actually measured I and V. It's I versus V. And there's a whole family of curves here. Right? There's all different data sets. And what the difference between the various data sets is the ones in the back that show this flat spot near zero voltage were on the wrong side of the critical point. Okay, no excitonic phase, just two independent layers. No current flows at low bias. Turn up the bias and the big peak appears, and then it collapses. Back over here, dIdV would be negative. Okay? But if I make the layers closer together, right there, this is a question about whether there's a phase transition or not. Right there at this critical separation between the layers, suddenly an anomaly appears, not suddenly, gradually, an anomaly appears at zero bias. That's the anomaly that's responsible for this Josephson-like peak, which I've colored red in this picture. So you can distinguish between the coherent part of the tunneling and the incoherent part. And if you go out here to these peaks and you look at the energy scale, they're fractions of a millivolt. Right? They're like half a millivolt. Half a millivolt is 5 Kelvin. This physics turns on at 100 millikelvin. These are very high energy processes. If you, like I said, you hit with a big enough hammer, you're going to break the thing. And that's really what's happening. So it's incoherent tunneling. Thank you very much. Thank you. That was fun. Right.